Everybody to lesson number 1 of Unit 7, sequences and series. So let's get right into it. We've got sequence, which is a list of numbers in a specific order, and a finite sequence, which is considering only the first n terms. Right? So if we don't know exactly how many terms we're talking about, it's just a sequence, but if we're talking about so many terms, it'd be a finite sequence. Okay, so real quick, a little bit of some notation here, right? You have this a with a little sub n. We're going to be replacing that n with a number when we do these problems, depending on which position in the sequence we are talking about. Okay, so this first problem says write the first 5 terms of the sequence. So if I'm talking about the first term, right, the first entry, we would be doing 2 times 1 plus 1, which is 3. If we do the second term, we're doing 2 times 2, right, plus 1, which is 5. And we're just going to do this for all 5 terms. So these are the first 5 terms of this particular sequence. We just want to list them 3, 5, 7, 9, and 11. And that's our solution. Okay, so I have one right here for you to try out. Very similar. Just be aware now that you have 2 different ends that you're going to be evaluating. So pause the video and resume when you're ready to check. Alright, let's see how you did in this one. For a first term, we're going to be doing 1 plus 1 divided by 1 squared. That's pretty much 2 divided by 1, which is 2. Our second term, we're doing 2 plus 1 over 2 squared, which would be 3 over 4. And we just keep on going in this fashion. Right now we have 4 over 9. This next one is going to be 5 over 16. And last, we get 6 over 25. So our final answer here, 2 3/4, 4 9ths, 5 16ths, and 6 25ths. Okay, those are our solutions. Okay, another example to look at. We want to write the first 4 terms of this sequence. A sub n equals -1 to the power of n times 2n. Alright, let's check this one out. Alright, so -1 to the first power, that stays as -1, times 2, that's just going to give us -2. And this is where this particular function gets kind of interesting. -1 to the second power, that becomes +1 times 4. We get +4. So we had -2, now we've got +4. Let's see what happens with our next term. -1 to the third, that's going to give us a -1 times 6. So we get -6. So now we're starting to see our pattern that we're going back and forth, and that makes sense with our powers here. So here is our sequence for the first 4. We've got -2, +4, -6, +8. Right, going back and forth. That's what that ends up doing for us. Okay. So one more for you to try. You're writing the first 4 terms of this sequence right here. Pause the video and resume when you're ready to check. Alright. let's check out how you did. So we're going to end up having -1 on top and 2 on bottom. That looks like as simplified as that's going to get. This is going to give us +1 over 3. Next, I'm getting -1 over 4. And finally, +1 over 5. So here's your solutions. -1/2, +1/3, -1/4, +1/5. And we can probably make some guesses, right? I mean, it looks like every even is going to be negative and every odd is positive, so we could predict what some of the future ones might look like. Okay, now we're going to do something a little bit different. We're going to be writing the expression for the nth term, right? So this was the expression of the nth term, right? This is the expression. Depending on what place we're talking about, we would have some sort of formula and we get a value, right? So now they're giving us what those values are. We need to try to figure out what that function is, basically, to get the next term. So this is what you do for these problems. They're not the easiest things in the world because really you're kind of comparing and guessing a little bit. It's really the easiest way to do these that I can think of is to compare them, right? So they gave us the first few terms, right, as 0, 3, 8, 15, 24. And then the position that each of those are in, right, this is our first position. This would be our second position, our third, our fourth, our fifth, and so on. So what I'm going to do is I'm going to compare what the number is compared to where it's located. And I'm going to have to kind of dig deep a little bit and think about something that I might notice. Right? For example, these all are almost a perfect square, right? If I had 1, 4, 9, 16, 25, those are all the perfect squares. But these ones happen to be 1 less. Okay, so it's 1 less than a square, and it happens to be in that position, right? So if I was to take my first position, square it, and then subtract 1, that would be giving me the answer for each of these particular spots. So this is the expression that we're looking for. Right? We squared our first number, subtracted 1, we got that number out. Okay, so it takes a little bit of thinking and recognizing patterns. So let's take another look at another one. Okay, we want to write the expression for the nth term of this finite sequence. Okay, so again, we're just going to compare each position. Oops. Okay, now I'm looking at this comparison, and right away I have 1 to 1. Nothing really is jumping out at me as far as this term, so I'm going to have to look a little bit further into the pattern. Okay, what I'm noticing is that I have a fraction first of all, so some different things are going to be happening. But on the top, it's only even numbers, right? This is 4, 6, 8, 10, right? So I'm going up by 2s. So it's an even number, and it happens to be twice whatever position, right? I'm in the second position here. If I double it, I get 4. In the third position here, I double that, I get 6. So I can see pretty clearly that it's going to be twice whatever on top. As far as the bottom, well, here this is 3, then I got 4, then 5, then 6, so it's only going up by 1. So when I look at the position, I notice second position, and now it's 3 on bottom. Third position, we got 4 on bottom. So really, it's whatever the position is, plus 1. Now, we just have to make sure that that works here, right? If I was to do 2 times 1, that'd be 2, over 1 plus 1, which is 2. So we had 2 over 2, that gave us 1 out. So it actually works for everything in this sequence. So that is the expression that we're looking for. So you have to be able to look at and compare some things in these. And if you have a fraction, you actually have 2 things that you're trying to figure out. Okay, so I have 2 problems right here for you to try out. Pause the video and resume it when you're ready to check. Alright, let's see. These are each of our numbers for the first expressions. I'm just going to write the positions underneath. Okay, so let's see. This 1-to-1, not really the most useful thing in the world. But if we start looking later on in the pattern, what I'm noticing is that these are going up by 2, it looks like, right? So it's going to end up being 2 times some number, but they're not even. So in order for them to be odd, we'd have to either add or subtract 1 to make them odd. So let's look at the position now. Right, if I was to take, I'm going to jump over this 1. If I was to double 2, which I know I'm going to have to in order to get that space of 2, that'd give me 4. And if I want it to land on 3, it's going to have to be 1 less. So this is my guess. And let's just check. If I double 3, that gives me 6. Subtract 1, that gives us 5. Does it work for the first position? 2 times 1 is 2, minus 1 is 1. This seems to work for every number. Let's check out problem B. By the way, you might notice that these are not simplified, and it makes it a little bit easier for these problems when you get into a college course. Usually the people who write the books aren't this nice. They simplify, and then you kind of have to think even harder about it. So be happy that these ones are a little bit easier to recognize. What I'm noticing, especially because I have fractions, I'm going to skip this first term for right now. Actually, I can look at the first term. Let's see what we've got going on. On top, I've got 1, 4, 9, 16, 25. That should go off right away in our heads as perfect squares. And it's the position as well, right? First position would be 1 squared. Second position is 2 squared. So I don't have to do anything to our n here. It's just squaring it. As far as the bottom, I got 2, 4, 6, 8, 10. So those are evens, and it happens to be twice the position of where it's located. So we've got 2n on bottom. That seems to work for every position. That's our expression. Alright, so now we've written out some sequences and we figured out the expression for sequences. Now we're going to look at some different types. We have something called a recursive sequence. Recursive sequences are actually kind of cool, and they end up giving you some really messed up sequences as a result, which is kind of fun to play with, right? A recursive sequence, the future terms depend on or use previous terms. You have to be given at least the first term, though. Okay, so here we have an example that's telling us to write the first 5 terms of the recursive sequence as long as the first entry is 4. And then they have a little bit more of this notation, right? Here you see that we have term a sub k. Next you notice that it says a sub k minus 1. So what this really means is if we're on position, let's say 5, we would need 5 minus 1, which is position 4. And as this says, we're using previous terms. So if I'm looking at term 2, which is the one that I need to find next, 2 minus 1, that's the first term. So I'm going to plug whatever my first term was in. Okay, that's how the recursive sequences work. So let's do this one out. We already know A1 is 4. That's given to us. If we're doing A2, that's going to be 2 times my previous term, right? Because that would be 2 minus 1, which is 1. So I'm going to plug in that value. And then it's going to be minus 3. So let's see. 8 minus 3 is 5. When I do term A sub 3, I have to do 2 times 3 minus 1. So we're looking at the second term. The second term we found to be 5. So I'm going to plug in 5. So let's see. That's 10 minus 3, which is 7. For A4, I have to use 4 minus 1. So the third term here is 7. So that's 14 minus 3, 11. And finally, for the fifth term, 5 minus 1 is 4, so the fourth term here is 11. 2 times 11, 22 minus 1 is 19. So here's our solution. We want the first 5 terms: 4, 5, 7, 11, 19. And like I said, these are not really like easy to recognize patterns of numbers, right? They're kind of like a messed up sequence of numbers. Anyways, here's another one that we're going to look at. Okay, we want to write the first 5 terms of this recursive sequence. So recursive tells us we need to use previous terms. They give us the first term as 5, and then they're telling us now, okay, so this is written a little different. Now they're saying k plus 1. So if I was looking at the first term, if I was to look at the next term, that'd be the second one. But then you notice that this is 1 less. So again, we're depending on the previous term. Okay. What exactly do I mean by that? Well, we already know A1 is going to be 5. It's given to us. So if I were to take A1, which is the next one that I want to plug in, that would mean K is 1, right? K is 1. So if I do 1 plus 1, that would mean I'm looking at my second term using my previous term, A1. So we end up getting 10 for our second one. If I'm using the third term, right, 3, that means that 1 more than K would have to be 2. So I'm using my second term. Second term here was 10. So 2 times 10 gives us 20, right? So basically we're just using the previous term each time still. It's just a different way that they wrote it. Why do they have to come up with a different way to write it? I have no clue. I'm sure that there's a useful reason for writing it differently, but as far as we're concerned, it's just a different way of writing it. Okay, so here's what we end up getting for our sequence: 5, 10, 20, 40, and 80. Again, kind of interesting, right? They're not increasing steadily, they're kind of getting further and further apart. Pretty interesting recursive sequence there. So you've got one to try here. You're going to write the first 5 terms of this recursive sequence. Pause the video and resume when you're ready to check. All right, let's see. Our first term, we had -3. If we're looking at our second term, right, A sub 2, we need our previous term, so -3, and then we're going to add 1. That's going to give us +6 plus 1, that's 7. Our third term, we need our second term. Let's see, -14 plus 1, that's -13. We need our previous term. It's going to give us positive 26 plus 1 is positive 27. And finally, our last term, let's see, that's going to be negative 54 plus 1 is negative 53. So here we go. Here's our solution. Negative 3, positive 7, negative 13, positive 27, and then negative 53. All right. Still not quite done yet, but we're getting through quite a lot of material, which is good. Okay, we've got something called summation notation. Okay, summation, as it sounds, sum, means that we're adding. So we're going to be adding the first so many terms of a sequence. And the way that it's written, they have this really cool looking sigma E thing, right? The bottom number is where we're starting. The top number is where we're ending. And then they give us some sort of function, right? They're giving us, we start with our first term, and then we're going to end up adding the second term, and then whatever the third term is, all the way till the final one. Okay, and here they have to give us some sort of function. This one, it just seems like it's the next number, which is why they're just adding the next digit. But when you look at some of our examples, this says we're doing 4 times whatever I happens to be. So we're multiplying here. And then we're going to have to add each of those terms together. Okay? That's how summation notation works. So let's take a look at this first one. I'm going to start with I being 1. So I'm doing 4 times 1. But because it's summation, I have to add the next one, which would be 4 times 2. And then I'm going to add the next one, 4 times 3. And I have to do this until I get to 5. Right? 4 times 4 and 4 times 5. So those are all the things that they're looking for me to add. Let's see. 4, 8, 12, 16, 20. And if we add all those together, we end up with 60. Okay, if you needed to use a calculator real quick for it, I suppose you can use that. If you can add them even faster, right? I can see this is 20, that's 20, that's 20, so I have 3 20s at 60. So hopefully you're starting to get better at pattern recognition as well with some of these. Okay, let's check out a different summation. They want us to find the sum from 1 to 4 of this particular pattern. So we're doing 2 times 1 plus 1 plus 2 times 2 plus 1 plus 2 times 3 plus 1 and 2 times 4 plus 1. So these are all the ones they want. We start at 1, end at 4. Let's see. 2 and 1 is 3. 4 and 1, that's 5. 6 and 1 is 7. 8 and 1 is 9. Let's see, 10, 15, 24. Okay, so I got one more for you to try right here at the bottom. Pause the video and resume it when you're ready to check. All right. You're going to be adding from 1 to 5, evaluating here, right? We've got, let's start with 1 squared minus 3 plus 2 squared minus 3 plus 3 squared minus 3, 4 squared minus 3, and finally plus 5 squared minus 3. All right, let's figure out what these are now. 1 squared is 1 minus 3 is negative 2. 2 squared is 4 minus 3 is 1. 3 squared, 9 minus 3 is 6. 4 squared is 16 minus 3 is 13. 5 squared, 25 minus 3 is 22. All right, let's see. So that's 20. That's gone. 33, 36, 39, 40. We end up with 40. Not bad, right? Actually kind of fun to do. if you're a nerd like me, I guess. Alright, you thought we were done, didn't you? No, we still got some stuff. Right, we've got finite series or nth partial sum, which is what we just did, right? We're just finding the sum of the first so many terms. So summation notation, nth partial sum, it's all the same, right? Finite series. But the important thing here is that we're talking about something called a series, right? A series basically is when we're adding all of our terms together. Then we have these things which are called infinite series. You might notice that what we've been working with so far have been only so many terms. But what if you wanted to add all of the numbers forever and ever in a list, right? Because we could continue to plug in. So we want to know what would happen if we plug in all of the terms. Well, I'm going to show you some pretty cool ones to start with, and we'll get you'll get deeper into this in higher level classes, but let's take a look at some cool tricks first, right? If you have a repeating decimal of a digit from 1 to 8, we can convert it to a fraction with a denominator of 9, right? So let's say, for example, if we have 3 repeating, that's the same as 3 divided by 9. If we have 2.4 repeated, here's what's happening here. Okay, we take 2 times 9, whatever our lead digit is, and then we have this 4, which is going to be repeating. So 2 times 9 is 18, plus 4 ends up being 22 over 9. Okay, here's another example of the same idea, right? If we have 5.7 repeated, I'm going to take 5 times 9 plus whatever is being repeated. So we've got 45, right? 5 times 9 plus this 7 is going to end up being 52 divided by 9. So it's actually kind of cool when you see a repeating decimal. Whatever you take in the front digit times 9 plus whatever this is, that's as a fraction. That's kind of a cool trick to me. Okay, so we're going to use that in these problems down here. And what's really neat is that you're going to see that even though we're adding an infinite number of things, we're going to end up having a solid number, like one number. It's not going to be something going on forever. It's actually going to add up to something, which is neat. An infinite number of things adding up to something. Alright, enough of me blabbing. Here's what we're going to do. We're just going to do a couple of terms and get an idea of what's going on. Because we're obviously not going to sit here to do all infinity. So let's take a look at these first 4, right? If we have 7 over 10 to the first, that's 7 over 10, which is really 0.7. If we do 7 over 10 squared, that's really like 7 over 100, because when we square 10, that's 100. So now we're getting 0.07. If we do 7 over 10 to the third, that's like 7 over 1,000. So that's 7 thousandths, so 0.007. And last one that we have on this list, it's 7 over 10,000, so that's 7 ten-thousandths. And it's just going to keep on going on. So what's happening here? Well, it looks like we're putting a 7 in each of the next digits. And if I add this here to here, it's just going to fill in. And then these two are going to fill in. So basically, what we end up with is 0.777 repeating, right? So now we have that repeating decimal, which allows us to use our cool trick, right? It's just going to be 0 times 9 plus whatever this is that's repeating. So 0 times 9 is 0, plus 7 would be 7 divided by 9. That's our answer for that one. So you're going to try finding the sum of this infinite series. You can use the cool trick if you'd like to. Pause the video and resume it when you're ready to check. All right, let's see how you did here. You got 2 over 10 to the first, plus 2 over 10 to the second, plus 2 over 10 to the third, plus 2 over 10 to the fourth, right? And basically what's happening with these is we're getting 0.2, 0.02, 0.002, 0.0002, right? And we do this forever and ever, but what we're basically getting is this repeating decimal of 2's forever and ever. So if I was to do 0 times 9 plus whatever this is that's repeating, that's going to give me 0 plus 2 would be 2 over 9. That's your solution. That's it. That's it for this lesson. You made it all the way through. Hope that you enjoyed this, because this is actually one of my favorite types of math to do, is these summations and sequences and series. They're really just kind of fun to play around with, just checking out series and sequences of numbers. If you agree, leave a comment or bring that with you to class. Maybe if you have any questions, bring them to class or leave them down. Maybe somebody in the internet world can answer it for you. Until next time.